Hey, in this second section of our electrons, so we're on electrons still, but we're on section 2, and in it, what we want to do is kind of refine our model of the electron and what we think of our electronic structure around our nucleus. So one thing we talk about is we talked about the photoelectric effect in the last podcast, and really we had two equations we are looking at. We are looking at the energy of these photons of light. So photons are really, sometimes we would call them quanta. So quanta just means a packet, really a packet of energy traveling on this photon. So the quanta is the energy, and it's traveling on the photon. And remember, the equation for this was H. And that's really the particle. If we're thinking about a packet or a quanta of energy, a specific set, that is really the particle nature of light that we're thinking about. But remember, what we can do is we can relate this. It's a Planck's constant times the frequency. So the energy and the frequency are related, and frequency really is a function of a wave. It's talking about how many cycles per second, but what we're seeing is those cycles per second, that wave ability of that packet, that wave ability of light is related to its energy and how much quanta it can carry. So we have those two relations within one equation. We have the particle nature of light, and we also have the wave nature of light. And now what we're doing in this section is we're going to an idea by de Broglie. So Louis de Broglie. And what he's told us is, so the wave particle nature of light had already been discussed by Einstein through that photoelectric effect in Max Planck. But now what he did is he took that Bohr's quantized orbits of, say, a hydrogen molecule or a hydrogen atom that we looked at, and he's related that nature of light to any small particle, really any matter, but particularly small particles like electrons. So he told us that electrons in these orbits, the reason why that Bohr diagram doesn't really work when we get into larger and larger atoms is because our electrons aren't behaving purely as particles, but electrons can behave as particles, or they can behave as waves, just like our photons of light. So light is behaving as particles or waves, while our electrons can behave as particles or waves. What that means is our idea, our atomic model where our electrons are, just got a little bit more complicated. So here's what he gave us. He gave us this equation where we have our wavelength of light. So this is a wave of light. But notice what he's relating it to. Now v here is velocity. He's relating it to mass times velocity. And if you remember from your 9th grade science, this is momentum. So the momentum of the particle, the momentum of that electron is related to the wavelength of it. So really, really crazy that every particle, so not just light, but every particle has a relation between its particle nature and its wave nature. And so he gives us an atomic model that really we start thinking of more like this, that we have to think about these electrons in their orbits, but they're in oscillating orbits. So they're not just in kind of planetary orbits, but oscillating orbits. And we're going to see here really soon that this is going to get even more complex. So he extended the concept of wave-particle duality from photons to include all forms of matter, and particularly electrons, in a Bohr model of an atom. And so he gave the start of wave mechanics, of starting to try to figure out where the electrons are around the atom, but we have to think about it now in terms of waves. This is a quick kind of, we're flying by people here, but now we're getting into what this is Heisenberg's uncertainty principle. And what he told us about this wave-particle duality is, if we have wave-particle duality, then it's always going to be inappropriate to say that we can, well, not inappropriate, maybe inappropriate is the wrong word, it's never going to be possible to know accurately or exactly both the location and the energy of these electrons that are in those orbits. Because what he was saying is that the uncertainty in the position of the electron, and again, remember we're talking about the electrons in the orbits around the atom, the uncertainty in the position of the electron times the uncertainty in its momentum, or its energy. So we have position represented by x, we have p, which represents its momentum, its mass times its velocity. That those multiplied together have to be greater than or equal to basically this constant. So it is a constant value. So we have a constant over here. So what does that mean? Well, that means if the change in x of this gets bigger, so if we have more uncertainty in our position because our change of x is bigger, well, then we know our energy better, and that gets smaller. So the way we kind of think about this, so these are kind of inversely related. Again, this delta symbol means change in. So as the change in gets bigger, as how accurately we know its position gets bigger and bigger, so we know its position less and less and less, well, then we know its energy more. Same thing would happen if we flip those around. But how we like to think of it is, say we are looking at an electron, and we want to know what its location is. So just like in the photoelectric effect, maybe we'd hit it with a certain wavelength of light to try to eject that electron so we know where it is. Well, we hit that electron, so now we know how much energy it is, because we know how much energy of light we have to put in to eject that photon, but now we changed its position, because it has a new path and a new velocity. We've kicked it out. Maybe we've actually ionized that atom by kicking it out. So we know what the base energy, maybe we'd call our ground state is, so we know what the ground state energy level is, but we know how much energy is associated with that, but we don't know its location because we moved it as far as looking at that electron. Now, we can think about it kind of the other way, that if we want to find where it is, so we'd cool that element down to try to slow down those electrons so we could see where they are. Well, if we cool it down and slow it down, then we've changed its energy, right? So we can't investigate both of those. All we're going to ever know is we want to try to reduce their uncertainties. Doing that gives rise to wave equations. And what wave equations are, and they're based on Schrodinger's work, really our wave equations give rise to three-dimensional probability graphs. Our three-dimensional probability graphs where we're trying to find the location of the electron. So what we get when we do this is we get probability graphs, or probability information here based on those Schrodinger wave equations. And again, we don't need to know how to use or manipulate any of those equations, just what is giving rise to these probability graphs. So we have a probability graph of where this electron is. So if we assume the nucleus is in the center, this is a probability graph, and it's highly idealized about where that electron might be. And again, this electron has these various states because it's operating as a wave and not just on a circular orbit. So our electron is not spinning around this orbit at all. It is functioning as a wave and moving kind of in and out around the nucleus. And so what we get is that gives rise to a distribution chart like this. That if this is the nucleus, this is the most likely location of electrons around that nucleus. So we get a certain distance from the nucleus that tells us where those electrons are going to be. So that's the most likely location of that electron. So this might be 90% of our electrons are a certain distance from the nucleus. So here's another way to think of it, if you like apples and trees, that if we have this apple tree here and it's dropping its apples, and we made certain energy rings around this tree, well, we could measure the distance from the trunk and the probability of where the electrons, where the apples are going to fall. And then we have a certain graph that says, well, the apples, look at, I'm confusing myself, are most likely going to be within a ring, somewhere around right there. It's the most probable location of finding an apple around the tree. Now, notice there's some way out here, and they might be out there, but that's not the most likely area. Likewise, they're probably not going to be right around the trunk, not right on top of that nucleus or center of the trunk. That's probably not going to be a very likely place either. So in the first energy level of any atom, we're going to find, electrons a certain distance from the nucleus. What that does is that actually gives rise to probability graphs as we go further and further out from the nucleus, where we start seeing higher and higher energy levels. And at these higher and higher energy levels, what we'll see different nodes or peaks in our probability graph. So this is a probability graph for a 1s orbital. And right now, we're going to get into what a 1s orbital is. Right now, just look at this probability graph. So this is telling us what the likelihood of an electron in the first energy level is. Well, we get up to the second energy level, we're trying to find electrons there. Notice they could even be down where mixed in with the first energy level electrons, but the most likelihood is where this peak is going to be. So notice what that gives us. That gives us this idealized notion of what an atom looks like, where we have these spheres, or sometimes you might have seen images that looked more like this. And so here's where we kind of have a probability diagram of where this first energy level might be, and as we get out, we're going to see certain concentrations around that and around that. So that idea works really well when we have like a hydrogen nucleus, with like a really small atom that only has one electron. We can look at that probable location based on our Schrodinger's wave equations, say 90% of the time the electron's within this sphere. That gives rise to a graph like this, so that's our most probable distance. And so we say, yeah, that element kind of looks like this. Well, again, they're not hard spheres, and they're not even with, the electrons aren't even confined to that sphere at all. It could be with outside, but 90% of the time, the electron's going to be within that sphere. What we'll see then from these probability graphs is when we add in 2 electrons, we get this little sphere, that 90% of the likelihood of finding the electrons within that sphere. And we go into the next energy level, which is called our 2s energy level, and we'll find another sphere of probability. And again, remember, these things are being cut in half. So it's not a ring, right? It's a sphere that's been cut in half. And when we cut it in half, well, we see a smaller ring, and we see another ring further outside. Now, though, we get a little bit beyond into the second energy level, and then we see these weird nodes. And then notice in the 3s energy level, we see another kind of sphere, circular shape, and then you go beyond that and we get these crazy things. And so what we want to look at is what are these, and how do we describe what these shapes are? Because now we're not talking about spheres and orbitals anymore. Now we're looking at different types of shapes. So in the next half of the podcast, here's what we're going to do, is we're going to look at our 4 quantum numbers. We have N, L, ML, and MS. And what those are going to define for us is those are going to tell us where the electrons are as far as energy level, and in what probability graph, what shape they're in, what orientation they have, and what the spins on the electrons are going to be.